Right, in this question we're going to be looking at the January 2010 paper, question 5, and this question is focusing on diffraction, specifically on young slits and things like fringe spacing, distance to the screen, etc. So, to start off, the question says that when Thomas Young demonstrated the interference of light by illuminating two closely spaced narrow slits with light from a single light source, what did this suggest to Young about the nature of light? And so basically this is asking you to say whether this experiment suggests that light has a particle nature or whether it has a wave nature. And the way to think about it is, if you imagine that we've got our slit, so there's one slit, there's two slits, we've got our screen that's a massive long distance, several meters away. If light travelled as particles, then as your particles came towards these slits, pew pew pew, only the particles that are coming in the plane of the slit are going to be able to make it through. And so the kind of pattern that you would expect to see on the screen would just be two lines, two maxima, two bright spots where the light was making it through. The fact that we end up getting this series of maxima and minima, so this fringe pattern on the screen, suggested to Young that light had to be travelling as a wave. So it suggested that light travels as a wave. Now, in part B, it's saying the demonstration can be carried out more conveniently with a laser, and it produces coherent, monochromatic light. And it wants you to state what is meant by monochromatic. Well, remember that mono, think of monocle or monorail, just means one, and chromatic, chrome, means colour. And colour is, of course, distinguished by its wavelength. So monochromatic just means that it is light where the source emits one wavelength of light. Okay, and what is meant by coherent? Well, in a coherent light source, our source emits light with a constant phase difference. And if it were a 2-mark question, just for that bit there, you could also say that they have the same frequency, same amplitude. So, monochromatic, one wavelength of light; coherent, light that's being emitted with a constant phase difference; and if we want a more padded out answer for that, the same frequency and the same amplitude. Now, state one safety precaution that should be taken when using a laser. It might be obvious, but do not look at the laser. Other answers that you could have in there would be to use appropriate safety goggles, or don't shine the laser directly at somebody, or don't allow it to reflect off a surface and back towards someone, or make sure that hazard signs and safety signs are up. But the easiest one to remember is never stare directly at a laser. Now, part C is giving us the diffraction pattern that Young got from one of his experiments. Okay, and we can see here we've got our central maxima. Okay, that would be our nice big bright central maxima. And then we've got a next maxima there, the next maxima there. We're told that the slit spacing is 30 0.3 millimeters. So we know that that is our S, our slit spacing. But we also know that 0.3 millimeters needs to be converted into meters. So we need to have that as 0.3 times 10 to the minus 3 meters. And we're told that the distance from the slits to the screen is 10 meters. And that distance always has to be pretty big in order to get the effective fringe separation on the screen. Now, the question's asking you to use that drawing there to calculate the wavelength of the light produced by that pattern, or that produced the pattern. So we need to work out the fringe spacing, and to do this we need to look at the number of gaps we have, because remember, the fringe spacing, okay, our W, is the distance between our maxima. And be careful here, because if you look, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 maxima, but there are only 1, 2, 3, 4, 5, 6, 7, 8 fringe spacings. So we know we have 8 times our W is equal to 0.16 meters, and therefore we know that W on its own is going to be 0.16 divided by 8, which is 0.02. And now all we have to do is plug that in to our fringe equation. So we know that our fringe equation tells us that the fringe spacing is equal to the wavelength times the distance to the screen D divided by the slit separation S. But we want the wavelength, so we need to rearrange that equation to get it in the form of lambda equals fringe separation times slit separation divided by distance to the screen. So we plug our numbers in. That is equal to our fringe separation of 0.02 meters times our slit separation of 0.3 times 10 to the minus 3 meters. Remember, we converted that up here. All divided by the slit separation of 10 meters. And we end up with a wavelength of 6.0 times 10 to the minus 7 meters. Now, being at 10 to the minus 7, that's the same as saying 600 nanometers, 600 times 10 to the minus 9, so it would be in the visible light spectrum. The final part of the question is saying that the laser is replaced by another laser emitting visible light with a shorter wavelength. State and explain how this will affect the spacing of the maxima. Well, if we look at our equation, we know that wavelength is equal to fringe spacing times slit separation divided by the distance to the screen. And we know that these two are constant. That's a constant and that's a constant. If I'm emitting light with a shorter wavelength, so I am making that smaller, what effect's that going to have on W? Well, if those two are constant, in order for the equation to work, our fringe separation has to go down as well. So the first thing to say would be to say that the spacing would decrease and to get your second point, you could say anything from Looking at the equation, if you reduce the wavelength, you reduce the fringe spacing, because we know that the slit separation and the distance are constant. Or you could just say that wavelength and fringe spacing are proportional. So there we are, a Young's double slit diffraction question. Not too difficult, I hope, and I hope that's been helpful.